Hey guys, how's it going? So, I am a person who is not very comfortable with proofs, but ever since I started taking a course called number theory this semester, which basically means the study of numbers, I've gotten more and more comfortable with proofs. Like, for me, like I've learned that proofs, it's just you just got to do more and more of them in order to get comfortable with them. And I've always been interested in number theory, like ever since I was a kid. I was the one who learned myself in grade 8 that adding two numbers, like if the sum of a two-digit number or of any digit number is divisible by 9, then that number itself is divisible by 9. I didn't know that there was this thing called mod 9 at the time, but I'm pretty proactive in this course. And I finally found this was my very first proof that I was comfortable doing and giving an adequate solution to it. So the question is, let a and b be positive integers such that 3 to the power of a minus 3 to the power of b is equal to 3. Find all solutions of a and b that satisfy this equation or show why there are none. Now, the answer is actually there are no solutions. I have two solutions, two ways to solve this problem, an easy way and a long way. But before I start, I'm gonna show you how not to do it. Here is a common fallacy in math, and it's called proof by example. When you say proof by example, you give an example of how there's no solution here, but that doesn't, it's not an exhaustive case. It's like, it'd be like explaining this in the general sense. Like, let's say that, let's say here the example was, I saw a murder in my neighborhood. And then by this conclusion, by this example, I conclude that all people are bad. I don't think I need to point out the problem with this statement. Obviously, this is not true. This is not exhaustive. This is just based on the person's experience. This is not indicative of all the 8 billion people in this world. So proof by example is not a way to go. Obviously, we wouldn't follow this in real life. Maybe in real life, if we found like a lot of solutions, like let me say, we found a lot of solutions that led to the same conclusion, we would think that's true, like e.g., and it might work. I'm not saying that it will work. Let's say I can't find my keys in my room anywhere. And I looked exhaustively. This is a better proof by example, but it's entirely possible maybe you like missed like a tiny spot, maybe behind a cupboard or something. So this is slightly better than the first case, but it still, again, it's proof by example and it won't work. So now that I showed you how not to do it, let's show you how to do this problem. First of all, you should be able to recognize that this is a very good question. There are no solutions. Okay, let's begin with the hard way, just because why not? And we're gonna do this prove by induction and contradiction. Contradiction and induction. Contradictions are indirect proofs where you show the opposite is false. So let's assume there is a solution to this equation, first of all. Okay. Okay, so first of all, alpha has, sorry, not alpha, A. First of all, A has to be greater than B. Or because otherwise you'd end up with a non-positive solution. A non-positive value for 3 to the A minus 3 to the B. Because because A and B are positive integers, and if A is less than B, then like this expression will obviously be negative. And if A was equal to B, then you get 0. So it would never be positive, hence never equal 3. So A has to be strictly equal to B, assuming there is a solution to the equation. Second of all, if A was equal to 1, then what you would get is 3 minus 3 to the B is 3, and 3 to the B is 0. But that's a contradiction because there's no positive value B that satisfies this equation. So you get a contradiction, which is written something like this. So A can't equal 1. And there's no value B for A. So A cannot equal 1. Okay. Now, if A equals 2, I already said that A has to be greater than B. So, and A and B are positive integers. So B has to equal 1. That's the only available solution. If A is 2 and B is 1, you get 3 to the 2 minus 3 to the 1, and that would equal 6. That's not 3. So once again, that means A cannot equal 2. Here's where things start to get a little interesting. Let's look at the case A is equal to 3 now, okay? So that means B can either equal 1 or B can equal 2. But here's the thing. I already know that B cannot equal 1 because it did not work for when A is equal to 2. If it didn't work for A equals 2, it's not going to work for the value A equals 3 because it's just going to create a bigger difference, a number like it's just going to create a number bigger than 6 if A equals 3 and B equals 1. And we already showed that 6 is bigger than 3. And when A is 3 and B is 1, that value will be bigger than 6. So B can't be 1. And if B equals 2, then if B is 2, then like, let's see, 3 to the 3 minus 3 to the 2 is 18, which, sorry. No, that's true, yeah, which is not equal to 3. So once again, A cannot equal 3. So for A is equal to 4 onwards, like here's the pattern. Here's the supposedly the induction way you can do it. You can eliminate all values of all possible of B for each A between 1 and a minus 1, because remember a is bigger than b. You can eliminate all possible values except for b is equal to a minus 1. So because if b was not, so if the b values, the earlier b values didn't work for the earlier a values, they're not going to work for the later a values. So like, for example, if a is equal to 4, you can eliminate, you can exclude b equals 1 and b equals 2, since they will just give a bigger difference. Then when a was equal to 3, and the difference was already not equal to, and the difference was already bigger than 3. So like, and for example, if let's go try a bigger one. If a is equal to 9, you can eliminate, exclude b equals 1 to b equals 7, since they didn't work for the first 8 values of a. So like, that means we can exclude all values except for the case when b is equal to a minus 1. Now let's consider the general case where b is equal to a minus 1. Okay, then you get 3 to the a minus 3 to the a minus 1 is equal to 3. Okay, so then you get, what is it? 3 to the power of a minus 1. That would be a 3. And that would be a 1. So that's times 2 is equal to 3. 3 to the a minus 1 is equal to 3 over 2. But like right there, there's no possible a value, right? So no a value works. And that's a contradiction. So hence, there are no solutions. To the equation 3 minus a, 3 to the a minus 3 to the b is equal to 3. And we are done this proof. I believe it's a box to show you're done the proof. Now there's a much, much, much faster way to do it. I didn't want, like, the reason I didn't show this earlier was because I didn't want to like share this proof and then you guys like says, oh, I know the proof now, and then just left. There are oftentimes more than one way to do a proof of things. So here's the second way, and it's much easier. I should have just cut this part out, but it's too late now. Live and learn, guys. Live and learn. All right, so part 2 is that 3 to the a and 3 to the b, this will like literally take 30 seconds. 3 to the a and 3 to the b are odd integers. The statement from our previous reasoning, like from solution 1, is still true. A still has to be bigger than b, or else you get non-positive values, okay? But we'll keep that in mind for later. Now, generally, the rule is if an odd number, to a positive integer power is still odd. I'm not going to prove this theorem, but it's true. You can just say 2k plus 1 to the power of n, where n is bigger than 0 and is a positive integer, and k is like an integer, and you can just use the binomial expansion. I'm not going to show it here, but it's true. You're going to get an odd value for this. So yeah, this is true. So then we're done. 3 to the a minus 3 to the b would be even, because 3 to the, think about it, 3 to the a odd number minus odd number is even, right? But 3 is an odd value. So like 3 to the a minus 3 to the b is even, and 3 is an odd value. Even cannot equal odd. So there's a contradiction. Hence, there are no proofs. Hence, there are no solutions. To this equation. And we are done much faster. All right, so that is all for today. I hope you guys enjoyed this video. I'd love to stay, but for now, I have to jump. I'll see you guys on the other side of the bridge. Catch you next time.